So this says, for the following exercises, use the second derivative test to identify any critical points and determine whether each critical point is a maximum, minimum, saddle point, or none of these. And that just simply means inconclusive. Now again, in the last video, I talked about the second derivative test, and that was this here. So we're looking for D here to start with. And so that means we're going to need our partials with respect to x, our partials with respect to x twice, and our y's, an xy, and we need a fyy. So we're going to do a lot of partial derivatives here to get started. So that's what we're going to do first. So I'm going to start with fx first. And that's going to be 2x minus 6. And that's it. Everything else after that are constants because there's no x's in any of those. So they're all considered zeros when I take partial derivatives with respect to x. So now fy, that's going to be 0, that's going to be 0. So 2y plus 4, and that's a constant. So now I need fxx, because that was another one I needed. So I'm going to do that one here. And that's just going to be 2, because I'm going to take this one here and take the derivative of that one, and that's going to give me just 2. And then the same thing for fyy, I need that as well. So I take the derivative of, let me be specific here, 2y minus 4, and that's going to give me 2. All right, and then I need fxy. That's another one I need, so I'm going to draw that one down here. So fxy. So I'm going to take this one here, and with respect to y. And that's going to be 0. Because there's no y here, so that's considered just all a constant, considering where y is at. All right, so there we go. That's everything we need. Now the formula, and I'm just going to write that formula here, so that dxy, that's going to be fxx. So that's, I'll write the formula first. And I'm not going to put any of the all the complete notation here, just kind of a rough idea of what we're dealing with here. Plus, just so, this notationally is not correct, but I wanted just the idea of what I'm putting in where. So I'm going to be a little laxed about that here. And if you did that on a test, I think I would be okay with that. I won't have an issue. Plus an xy squared. And that's just going to be 0 squared. So this actually turns out to be 4. So this tells me my d is greater than 0. So let's see what that means. All right, so I go back here now, and I take a look at this. And I say, hey, d is greater than 0. So now, when I find those critical points, because I need that too, I need to find out where those are 0 at, then I can go further here. So I did find d though. Maybe I should have done that right away. I'm not sure what order that should be in, but I know d is greater than 0 now. So now I need to find my critical points. So I have this fx, and I want where fx equals 0 at. So that would imply 2x minus 6 has to equal 0. And then my fy has to equal 0 also. And that's going to be 2y plus 4 equals 0. So now, again, this is a system of two equations, two unknowns. And I think, honestly, here, I'm just going to use the addition. Oh, those are y's. I can just solve these, actually. Solve both these equations. I was thinking way too difficult for this one. So then for the first one, I move the 6 over, divide by 2. I get x equals 3. Then I move the 4 over, divide by 2. I get y equals negative 2. So my ordered pair where both of these are 0 is 3, negative 2. So now when I plug that in d here, since d is a constant function, it's going to give me 4, which is greater than 0. So even for this point here, it's greater than 0. So now I can go further now. So let's go back. Here we go. So now we need fxx where we plug in that point at. So that's what I'm going to do now, because now that this is greater than 0, we have the critical point. So now we can get into this and say, okay, now I have to take that fxx. Now again, since this is a constant function too, I really don't have to do anything more. I can say it's greater than 0, but I just kind of want to show you the notation. So this is actually going to equal to, because fxx is a constant function, which is greater than 0. And since it's greater than 0, that means it's positive, which means that I can think of the idea of concave up, which tells me it would be a minimum. And that's really what I do. When I go back here, notice how this reads. D is greater than 0, fxx is greater than 0, so that means it's a local minimum. And thinking about the idea previously, concave up, it's got to be a minimum. Done. So that tells me then the point 3, -2 is a local minimum. Now we can't say it's the absolute minimum until we have further information. That's our only critical point. But so we'd have to possibly go a little further with it to truly understand it. Now it can be a little more interesting when we get more critical points instead of just one, like this problem. So I guess that may be a little boring, but that's our answer.